Good day everybody, we got a beautiful question. Foremost, we need to draw the figure. So let me do that. We got a quarter circle. This quarter circle is present inside a square. So the square is drawn. Okay, this is just an approximate figure. Now we got another quarter circle which we need to draw. Okay, now let me take this point as A, B, C, D. Since I mentioned to you it's a square, we need to complete that. That's the small circle. We are expected to find its area. Now a few things has to be mentioned. Now there is a point of contact here. So I've taken A, B, C, D. Let me take this point of contact as E. There is a point of contact here with the square. So there is a tangent there. Let me take that point as F. There is a point of contact with the second circle. Let me take the point as some H. Right, I'm taking it as H. I hope you can see that. Okay, let me draw it like that, H. Okay, now this is given. This sides of the square is given. Okay, let me write that down. This is given as 2 units. This is a solution. The sides of the square is given to be equal to 2 units. So this would mean this is going to be the radius, right, of the circle. So this would mean we have 2 circles. When I say circles, it means we are only dealing with a quarter circle. Quarter circles, right? 2 circles of radius is equal to 2 units. You agree with me? See, this is going to be the radius of the first circle and this is going to be the radius of the second circle. You can also mention this to be the radius. So we have a radius here, a radius here, a radius here for the first circle, the second circle, and more so this radius is also shared by circle 1 and circle 2. So having mentioned that, now that we know the radius of the 2 quarter circles, what we are going to do is we are going to use a theorem. Now we observe that the small circle has a point of contact, okay, C-O-N-T-A-C-T, okay, contact, as a point of contact. Let me take this circle 1, right, at D, at E with circle 1. I'm mentioning it as like this, circle 1, right? So we observe that the small circle has a point of contact at E with C1. So there is a theorem. This means if we were to draw a line through E, then the line would connect the centers of C1 and small circle. Let me write this down here. Small circle. So that is the most important concept you got to know. So if I were to draw a line through the point of contact, then that would actually connect the centers of the two circles. So this is connected A, and if I were to take this as some O, they are connected. So let me just write this down, O. So that's an important point. Now you might be wondering, why did I utilize that theorem? That theorem is the theorem that is going to help us in solving the question. Now from the figure, what do you see that? Or I should say, from this line also we now have, what do we have? AO is written as AE plus OE, right? Let the radius of the small circle be equal to R. So this would mean my AE is, this is the radius, right? AE is equal to 2 units plus OE is equal to R. So AO as a value now. Okay, fair enough. Now next thing, let us come to the second circle. It is connecting at C, right? This is the second quarter circle. Now there is a point of contact of the small circle with the second circle. So according to the theorem, if I were to draw a line through the point of contact, then that line would pass through the centers of the circles which are in contact. Meaning, if I were to draw a line like this through the point of contact of these two circles, and that would pass through O and B. So that's a very important point we need to bring it in play, right? That's critical for us. So what I'm going to do is I'm going to draw a line. So if I were to draw a line, okay, so that's how it looks. O and B are connected, O and A are connected. That's a key concept that would help us in solving the question. Okay, so having drawn that, what I wish to do is I would like to draw a line from O to the tangent at F. The small circle has a tangent at F. Now if I were to do that, that would have an angle of 90 degree. That's again I'm utilizing a theorem. So let me write that down. Let us now draw a line from O to the tangent at F. So as I mentioned to you, if I were to do that, an angle of 90 degree would be created. So it's actually a straight line. So have that in mind. So I am drawing a line from O to F. So figure is not to scale, right? So there is a 90 degree here. So this is 90 degree. Next, what I wish to do is I would like to draw a line from O to the radius AB. Now, why am I doing it? You would be asking me, why do I do that? I am doing it so that I would be in a position to apply the Pythagorean theorem. So what I wish to do is I would just state here, drop, or this is the best way to say, drop a line from O to AB meeting at, say, EFG, meeting at G. So if I were to do that, then I would get a 90 degree angle. So this is going to be 90 degrees. It's a perpendicular. So what I will say here is, instead of just saying drop a line, drop a perpendicular line. So this point is G. So this would mean OF is equal to GB, right? So this is going to be R. OF is equal to R, so this is going to be R, right? Okay, fair enough. Now comes the equation part. So probably, okay, I will just darken the point so that you can see that there is a rectangle there. Okay, so foremost what we are going to do is we are going to be considering AGO. Consider the triangle AGO. So this is what I am considering, AGO. Now since it's a perpendicular, 90 degree is being made here, right? So we can use Pythagoras. So by Pythagoras, what do I get? I get AG squared plus OG squared is equal to OA squared or AO squared, right? So you can write it like this. By Pythagoras theorem, we know that. So what do we know? We know that I can write it like this. Okay, I'll write it like this. AO squared is equal to AG squared plus OG squared. Now this would mean I can rewrite this as AO squared minus AG squared is equal to OG squared. Now you will know why I am writing it like this. You can see that in this particular figure, OG is the common line that is shared, or the common height shared by two triangles. So now I wish to consider BGO. So initially I considered AGO, now I am considering BGO. Now consider triangle BGO. Now clearly there is a 90 degree here, right? This is 90, means this will be 90, BGO. So by Pythagoras we can have an equation. By Pythagoras theorem we know that. So what do we know? We know that the hypotenuse, we started for this as AO squared, so we will start this as BO squared. So BO squared is equal to the adjacent, that's GB or BG squared. You can write whatever you want, BG squared plus OG squared. I have written it like this just to have some continuity or some consistency, because I have already taken here AG, so let me use BG, but it's up to you, it doesn't matter. So now what I wish to do, I would like to extract OGs from here. So this is going to be BO squared minus BG squared is equal to OG squared. So if I were to take this as 2, if I were to take this as 3, I can equate these two things, right? So from 2 and 3 we get, so what do we get? We get AO squared minus AG squared is equal to BO squared negative BG squared. Now what is AO? Now AO is 2 positive R, so just substitute that. 2 positive R, it has a square there. Now what is AG? Now as I mentioned to you, the side of a square is 2 units, so this entire thing is 2 units. Now OF is R units, so this is going to be R, right? Now but we need AG, we need this length. This entire length is 2 units, this is R, so this is going to be 2 minus R, right? So this is going to be 2 minus R. So substitute that. 2 minus R squared is equal to BO. What is BO? BO, this entire length is 2 units, right? This entire, because this is the radius, and we need BO. So what is BO? From 2 units, we have to subtract the radius here, right? If I were to take away from 2 units the radius, I would get this one. So this is going to be from 2, you take away R units. So this is going to be from 2, you take away that R, you get BO squared. Now what is BG squared? Now what is BG? BG is nothing but OF or FO. That's a radius there. So that's going to be R squared. So from here we need to get R. So how are we going to do that? We need to expand this. If I were to expand this, is going to be 4 positive 4 times R, positive R squared, negative, this is going to be 4 negative 4 times R, positive R squared is equal to 4 negative 4 times R, positive R squared, negative R squared. This and this gets cancelled. So you got a positive R squared, negative R squared, this will get cancelled. You got negative 4 and positive 4R and positive 4R, so it's going to be 8R. Positive 4, negative 4, that's gone. And over here I can bring this 4R to this side, so it's going to be positive 4R, this is going to be 4, that's 4 units. So therefore 12R is equal to 4. So R is equal to 4 over 12. That's going to be 1 over 3. The radius is 1 over 3 for the small circle. So radius is 1 over 3. So therefore area of the small circle is pi r squared, which is nothing but pi times 1 over 3 squared, which is equal to pi over 9 square units. So that's a solution for this question, everybody, and this is a lovely question, and I hope you enjoyed this. Please leave your likes and subscribe. Thank you. Enjoy your day.